In roughly 5 hours, a broad and serious weather setup begins placing 26 million Americans under a severe weather threat. Across drought-split counties in Texas, 8 to 10 inches of rain may fall by Sunday morning. Farther north, near sundown over southern Canada, a tornado parameter more typical of a much more volatile setup is appearing in a place and season where operational forecasters do not expect to see it often. At the same time, 6 western states are dealing with critical fire weather, while 18 river flood warnings remain in force across the Central Plains, with several raised to moderate severity overnight. And beyond the immediate danger, the European weather model is pointing toward the possibility of a tornado outbreak across Minnesota and Wisconsin on Wednesday, arriving just as the first significant heatwave of summer settles in behind the system. 6 storms, 1 larger pattern, and a 9-6-hour window. If this is only coincidence, it is an unusually tangled one for forecasters to explain. If it is not, then the larger question becomes simple and unsettling. What is the atmosphere trying to organize? If you are following this unfolding compound week, stay with Calm Space as we track it step by step. Tell us where you are watching from and which of these hazards is nearest to your zip code. Sharing this helps the Calm Space community grow. Now we begin with the first key idea. There is not just one storm. For a moment, set aside the individual headlines and look at the whole map at once. Over the desert of West Texas, a slow-moving upper-level low is sitting in place and beginning a patient drift toward the northeast, as though the atmosphere has no reason to hurry. North of that, a strengthening shortwave trough is carving into the Great Lakes and pushing a cold front toward air east of the Mississippi that has been trapped in the 80s and 90s for days. Then, farther north again. Across the international border in southern Saskatchewan and southern Manitoba, the high-resolution rapid refresh model is showing a significant tornado parameter value that one operational forecaster described as something not seen in that region for a very long time. Meanwhile, hundreds of miles to the south and west, 21 red flag warnings are spread across 6 western states where humidity has dropped into single digits and wind gusts are reaching 40 miles per hour. Behind all of this, the water story has not ended either. The Missouri River, the Grand River, and the Platte River continue rising across Missouri, Kansas, and Nebraska, with 18 separate flood warnings still active and several of them increased to moderate severity while many people were asleep. This is not a future scenario or a distant forecast graphic. It is the current snapshot as this episode goes live, and that matters because the atmosphere is already loaded before the next chapter begins. If someone had tried to describe this exact arrangement last Tuesday, it might have sounded like a summary of the worst week of the summer. Yet this is not even a full week. It is one Saturday morning, and the next 96 hours have barely started. The part that can be easy to miss is that no single storm is responsible for all of it. What we are seeing is a broader pattern producing 6 separate weather hazards in different regions of the continent at the same time, each connected to the same upstream atmospheric configuration. There are damaging wind thunderstorms aimed at the Ohio Valley and the Northeast. There is the slow upper low over Texas, capable of delivering 8 to 10 inches of rain onto drought-cracked ground by Sunday morning. There is a possible large tornado outbreak over the Canadian prairie this evening. There is critical fire weather across 6 western states that may persist for days. There is the Central Plains River flood disaster that has not really disappeared from the map because it has not truly ended. Then comes the next reload. Severe weather on Tuesday and Wednesday across the northern plains and the upper Midwest, with the European model far more aggressive than the American one, and with some forecasters quietly discussing tornado outbreak potential across Wisconsin and Minnesota. And behind that, by mid to late next week, the first significant heat wave of the entire summer is expected to lock in across the central and eastern United States. 6 events, 1 pattern, and 1 96-hour span. In a calm weather documentary, this is the moment to slow down rather than speed up, because the links between these hazards may be more important than any one storm on its own. That is why calm space does not simply chase the loudest storm on the map. The more revealing approach is to watch the full continent at once and ask whether events happening in distant places are truly separate, or whether they are different expressions of the same atmospheric machine. Hold that question close for the next 2 hours, because the setup now unfolding is not normal in the plain meteorological sense of the word. Not unprecedented in the exaggerated way that every dramatic weather event can be made to sound online, but unusual in the practical, climatological sense used by meteorologists who have spent 30 years learning what June usually looks like. June can bring compound severe weather weeks. June can produce tornado outbreaks, flash floods, and surface lows. None of those categories alone is shocking. What stands out is the simultaneity. 6 different kinds of severe weather igniting in different parts of the continent, all traceable back to the same upstream wave configuration within the same jet stream on the same map. That kind of alignment raises a larger question about how connected the atmosphere may be when the pattern is strong enough. It suggests that the map should be read less like a collection of isolated warnings and more like a single, moving system with many faces. So, we are going to move through this carefully, piece by piece, over the next 2 hours. First comes tonight's severe weather window in the Ohio Valley and across the Northeast, where the most intense period is expected between 3 and 8:00 Eastern Time, and where 26 million people sit under a slight risk for damaging winds. From there, we turn back to Texas, where the slow-moving upper low may pour enough rain onto drought-baked ground to create one of the worst flash flood corridors of the early summer. Then the focus shifts north to southern Saskatchewan and southern Manitoba, where the significant tornado parameter is behaving in a way that is not typical for early June. After that, we examine the river flood disaster across the Central Plains, a situation that never fully ended and may be recharged by Tuesday's incoming surface low before the rivers have time to recede. We will also outline Sunday's reload and Monday's more intermediate quiet, but the deepest attention belongs to Tuesday and Wednesday, because the multi-model convergence on Wednesday is the part of this story that may deserve the closest watch. In a setup this layered, the quiet intervals may be just as important as the violent ones, because they show how the atmosphere resets before the next wave arrives. Behind this entire setup sits a larger atmospheric architecture, a heat dome settling in behind the troughs, and a body of published science that may help explain why 6 separate weather threats can unfold at the same time. The key idea to keep in mind from the beginning of Part 2 through the end of Part 10 is that there is already a scientific framework for this kind of pattern. It is not a new internet theory, and it is not outside the mainstream. It appears in peer-reviewed work in journals such as Nature, Climate Change, Water Resources, Research and Communications, Earth and Environment. The term is quasi-resonant amplification. In simple terms, it describes a stationary, high-amplitude jet stream configuration capable of producing multiple extreme weather events, separated by geography, across the northern hemisphere, mid-latitudes, at the same time. The earliest papers on this are now more than a decade old, and the mechanism has been laid out in the literature. What is appearing across 6 different regions of North America this Saturday has the same basic structure described in those studies. Later, in Part N, we will slow down and examine that framework carefully, what the science says, how the mechanism is described, why the next 96 hours may resemble its operational expression, and where reasonable objections can still be made. That last point matters. There is also a completely fair way to read the coming sequence as nothing more than a very bad week, because very bad weeks have always existed in the weather record. The 2010 Millbury, Ohio, F4 tornado occurred on this same calendar date 16 years ago, a reminder that compound severe weather in June is not without precedent. So we will hold both possibilities in view, as calm space always tries to do, and let the evidence carry the weight. For now, simply notice the outline. 6 events, 1 broader pattern, 96 hours. The events are not hypothetical, and the pattern is visible. The deeper question is whether their combined meaning exceeds the individual pieces. In every continent-scale severe weather episode, there comes a quiet moment when the whole map can be seen at once, and the map seems to be behaving in a way that asks for interpretation. You can separate the Ohio Valley, Texas, Saskatchewan, Western fire weather, Central Plains flooding, and the Tuesday-Wednesday reload into 6 independent stories. Or you can look at them as one atmospheric arrangement and ask what that arrangement is doing. We are going to take the second path now. After all the build-up, it is fair to ask where the concrete details begin. They begin here, with Part 2, Saturday night, and more than 26 million Americans in the risk area. The Storm Prediction Center issued its Day 1 outlook shortly after 7:00 Central Time this morning, and this is the starting point, because it overlaps the largest population concentration. A slight risk zone runs from central Indiana through the upper Ohio Valley and into southern New England. Slight risk is Category 2 out of 5, which can sound restrained until the cities beneath it begin to add up. Columbus is included, so are Cleveland, Pittsburgh, Toledo, and Akron. Beyond that, the broader marginal risk reaches New York City, Philadelphia, and Detroit. Even if the most intense storms remain concentrated around the Ohio Valley and western Pennsylvania, the wider threat area involves 26 million Americans before the marginal zone is fully considered. The atmosphere is being shaped by a deepening upper-level trough digging into the Great Lakes during the day. This morning's water vapor loop shows the signature clearly, a curling, strengthening feature over the eastern half of the country. Ahead of that trough, mid-level speed maxima are moving eastward across the upper Ohio Valley and into New England. The SPC describes this as strengthening large-scale ascent. Put more plainly, a broad column of air ahead of the trough is being lifted again and again across a wide region at the same time. That lifting is occurring over an air mass that has spent days in the 80s and 90s, which gives the setup its energy source. The Boston area forecast discussion this morning describes a moderately unstable atmosphere with Cape values between 500 and 1000 Joule per kg, while some guidance suggests localized values may approach 1,500 JW per kg. The New York City office is examining Cape values from 100 to 500 JW per kg across the interior. Philadelphia's AFD notes low-level lapse rates of 7.5 to 8 degrees C per kilometer, steep enough to favor strong downdrafts and gusty winds from storms that form farther southwest. The Baltimore and Washington office expects mid-level flow to strengthen to 30 to 40 knots during the afternoon and evening, as the upper trough pushes height falls into the region. In practical terms, these ingredients point first toward damaging wind. Gusts around 60 miles per hour are possible, with isolated areas near 70 miles per hour, strong enough to break tree limbs, bring down power lines, and send unsecured outdoor objects moving. If you are inside the corridor just described, this is the calm but direct moment to secure trampolines, patio furniture, trash cans, and anything else exposed before lunchtime, because once storms organize, wind becomes the central concern. Hail is also part of the picture. The SPC highlights a focused 15% risk for scattered large hail, with the greatest risk across the upper Ohio Valley. That includes places such as Youngstown, Canton, and Pittsburgh. The reason is tied to storm mode. Early convection in this region is expected to include discrete supercells, meaning individual rotating thunderstorms before they have merged into a line. Those isolated supercells are the ones that can produce hail. Once storms become more linear, hail usually becomes less dominant. It is a subtle distinction on a map, but it can matter greatly on the ground. In the first part of the afternoon, roughly around 3 or 4 p.m. Eastern Time, there is a narrow period to watch before the storms begin joining into a more coherent squall line. That earlier phase is when hail is most favored. The practical expectation is quarter-size hail, though the strongest storms could briefly produce hail larger than that. If one of those early supercells passes directly overhead, the safest choice is to be indoors, away from exposed places and fragile surfaces. It is a small window, but in severe weather, small windows can still matter. There is also a low-end tornado concern, though it should be understood in proportion. The SPC shows a 2% isolated tornado probability, focused mainly from eastern Ohio into western Pennsylvania. That does not describe a tornado outbreak. In this setup, damaging wind is the main hazard. Hail comes next, and the tornado risk sits behind both as the low probability threat that cannot be dismissed. The reason is fairly straightforward. Wind shear may be strong enough to support discrete supercells, and those storms will be moving through a very unstable atmosphere. Under those conditions, 1 or 2 brief spin-ups remain possible. The most relevant window for any isolated tornado activity appears to be from 4 to 9 p.m. Eastern Time, especially along the eastern Ohio to western Pennsylvania corridor. It is a reminder that even a low percentage can still represent a real sky to monitor. One point deserves careful emphasis. Tornadoes in June are not strange for this region. Today, June 6th, is the anniversary of the Millbury, Ohio EF4 tornado of 2010, which crossed northwest Ohio during this same part of the year. So, when the tornado threat is described as low-end and tertiary, that should not be heard as meaning imaginary. It is a climatologically real possibility, just not the main character in this evening's atmosphere. The dominant storm behavior tonight is expected to be straight-line damaging wind rather than a broad outbreak of rotating supercells. That distinction may sound technical, but it shapes the way people should respond when warnings arrive. The broader timing of the strongest storms opens around 3:00 p.m. Eastern Time and gradually closes near 8:00 p.m. The morning may look disorganized, with showers and storms passing through that are mostly not severe. That can create a false sense of completion, as if the atmosphere has already spent its energy by lunchtime. But the more important phase comes later, as the sun returns and destabilization spreads from west to east, around 3. Discrete supercells may begin developing across the upper Ohio Valley. By 4 or 5, those storms should be starting to merge into clusters and line segments. By 6 or 7, bowing sections may be racing toward the I-95 corridor. By 8 or 9 inches the evening, the storms should be reaching the coast, with the threat easing from west to east overnight. The sequence is important because the atmosphere may appear quiet shortly before it becomes hazardous. Anyone with outdoor plans tonight needs to keep a close watch. The Memorial Tournament in Columbus will bring large crowds, and Columbus lies directly in the bullseye. The Governor's Ball in Queens will also need careful radar monitoring. People heading to the Yankees game in the Bronx on Saturday evening should check conditions before leaving home. The same applies to errands, barbecues, or any outdoor activity. This is the kind of afternoon when conditions can deteriorate not gradually over many hours, but sharply within minutes. In a particular zip code, a 1-5-minute span could take you from sun, warmth, and humidity to a downburst, producing 65 miles per hour winds. That is the failure mode here. Sudden wind, falling trees, scattered damage, and very little time to react. Have a shelter option ready, and have a reliable way to know when a warning is issued. the federal warning system will be operating. The more uncertain part is whether people will be listening at the exact moment it matters. The more technical side of this event explains why damaging wind is being favored over tornadoes. Tornadoes typically require a certain vertical wind structure, including sharp veering with height, stronger low-level shear, and a low cloud base. Thunderstorms that produce damaging wind lean on a different set of ingredients: steep lapse rates, dry air in the mid-levels, and an environment where descending air can accelerate as rain evaporates. Tonight, across the Ohio Valley and the Northeast, the atmosphere looks more like a damaging wind pattern than a tornado pattern because the low-level shear is modest. At the same time, lapse rates are very steep, and the dry mid-level column should favor downburst production when storms collapse. That is why the Philadelphia, Washington, and Baltimore offices are all highlighting wind gusts. The setup points in that direction, and the forecasts are reflecting it. Sometimes, the most useful forecast is not the most dramatic one, but the one that identifies the most likely way the atmosphere will cause harm. There is, however, one limiting factor worth flagging: moisture. Some forecast models suggest the air mass could turn out a little drier than expected. If that happens, convection may have more difficulty organizing, and the severe weather coverage could be reduced. The Philadelphia office specifically notes this risk, and the Boston office raises it as well. So the final extent of the severe weather partly depends on how much moisture is actually present in the air column when the cold front arrives. The forecast is built on the assumption that moisture will be sufficient. If the event underperforms, the reason may be that fewer storms form or organize than expected. If it performs as currently anticipated, the result would be the widespread damaging wind event the SPC is outlining. This is the quiet uncertainty inside the forecast, and it is worth holding in mind without letting it become an excuse to ignore the risk. It is easy to imagine someone in central Pennsylvania saying that tonight will simply be a bust. That possible failure mode is real, but the other side is real as well. The SPC has drawn a slight risk area. Many people are inside it. The timing window is defined, and the physical mechanism is present. In a situation like that, the safer assumption is not that the atmosphere will spare you. It is that the forecast could verify, and that preparation is the lower cost choice. If the forecast is wrong and nothing happens, you have lost very little. If you assume nothing will happen and the storms do arrive, the consequence could be a power line on your house. So, the practical response is simple. Behave as if the event will occur. Take it seriously, and move when a warning is issued for your county. That is the first of 6 concerns tonight. And while this cold front moves across the Ohio Valley, another connected part of the same larger pattern is influencing Texas in a very different way. The same upper low, helping to ignite those storms, is setting up a separate kind of hazard there. Part 3 brings us to Saturday over Texas, where the concern is not a fast-moving line, but a storm that slows down and lingers. There is a type of severe weather event that meteorologists may quietly fear more than the one drawing the loudest attention. It is not necessarily the bomb cyclone, and it is not always the tornado outbreak. It is the slow-moving upper low. The danger is subtle, because it does not have to look extreme to become serious. It does not need a dramatic central pressure, and it does not need to produce rotating supercells. It only needs to stop moving. When a slow-moving upper low lingers above an air mass carrying unusually high precipitable water, the danger comes from repetition. Thunderstorms do not simply pass through once. They can redevelop and move across the same ground for hours, each new cell laying rain over the track left by the last. In meteorology, that is the classic recipe for catastrophic flash flooding, and it is the same kind of arrangement that led to the Houston flooding over Memorial Day weekend a couple of years ago, as well as the Wimberley flood. Before considering any broader implications, that setup is already unfolding across central and northern Texas through Sunday morning. The upper low is now positioned over the Permian Basin in West Texas, and while it is edging northeast, it is doing so slowly. That pace matters. A fast system might sweep the storms onward. This one is crawling over an air mass with precipitable water values rising north of 2 inches. At first glance, 2 inches may sound modest. But for central Texas, in early June, it sits at the 95th percentile for the date. The air over the Houston metropolitan area is among the most moisture-rich that region typically sees during the first week of June. Any convection forming within that kind of environment can become highly efficient, meaning the storms may turn a large share of available water vapor into heavy rain over a short interval. This is the quiet mechanism behind a dangerous flood event. Not only how much moisture exists, but how effectively the atmosphere releases it. The immediate warning picture is already active. Just before 0 inches the morning Central Time, a flash flood warning was issued for southwestern Armstrong County and southeastern Randall County in the Texas Panhandle. Doppler radar shows thunderstorms producing heavy rain there, with up to 1.5 inches already measured inside the warning polygon. Before that warning expires at 12:45 inches the afternoon Central Time, additional rainfall amounts of up to 3 inches are still expected. That is the near-term, street-level part of the situation, the kind of alert that may reach your phone if you are in Amarillo. Yet the larger concern is unfolding farther south and east, across central Texas counties, where a flood warning remains in effect through 1 inch the afternoon for eastern Bell, Falls, southwestern Limestone, southeastern Lennon, northwestern Milam, and west-central Robertson counties. Low water crossings are already underwater. The process there is not fundamentally different from what is occurring in the Panhandle. It is simply broader, and the affected area is larger. Heavy rain is falling. Heavy rain has already fallen, and runoff is already moving through creeks, stock tanks, and smaller tributaries. Over the next 24 hours, those totals may become increasingly difficult to manage. This is where a weather event begins to shift from rainfall on a map to water moving through the landscape. The operational forecast for the next 24 hours is where the numbers become especially concerning. In the Fort Worth area, forecast discussion released at 5 inches the morning Central Time, forecasters described scattered convection with moderate to heavy rainfall continuing across the central Texas counties through the pre-dawn period. After sunrise, activity is expected to expand rapidly up the A35 corridor and become widespread. Most of Saturday's daytime convection is forecast to remain near and east of a 35, within a band of localized descent. By Saturday evening, the model guidance begins to point toward a more serious phase of the event. The upper low, the trough axis, and the anomalously high precipitable water values are expected to align in a way that supports widespread new convective development capable of producing heavy rainfall across western portions of North Texas. That activity may then train for several hours into Sunday morning. The key word is training. Convective training occurs when a line or chain of thunderstorm cells repeatedly crosses the same area, almost like rail cars moving along one track. One storm drops rain, then another follows over the same ground, and then another. The result is that local rainfall totals can rise much faster than they would from a single storm alone, because the measurement is not one isolated cell. It is the accumulated effect of a sequence. For flash flooding, that distinction can be crucial. So the important question becomes, how much rain could fall in the corridor where this training sets up? Here, the forecast separates into two different kinds of numbers: the headline amount and the reasonable worst-case signal. The official floodwatch messaging from Fort Worth is advertising 6 to 8 inches of rain through Sunday morning, with the main focus near and west of a 35 and near and north of a 20. That is the public-facing forecast. and it is the number most warnings are likely to emphasize. Even by itself, 6 to 8 inches in a single 2-4 hour window across urban and suburban North Texas would be an extreme flash flood producer. Rainfall of that magnitude over hardened, drought-cracked soil that has spent weeks baking in the sun can overwhelm low water crossings, underpasses, streams, creeks, and storm drains across a very large region. In other words, the official number is already severe before any higher-end scenario is considered. But the official number is not the ceiling. The higher-end signal comes from the High-Resolution Rapid Refresh Ensemble Forecast System, the HREF, specifically its probability-matched mean output, which is among the more aggressive guidance tools used operationally. For this event, the HREF probability-matched mean suggests a reasonable worst-case bullseye of 8 to 10 inches of rainfall in the 35 to 120 quadrant through Sunday morning. The Fort Worth office is using the more conservative 6 to 8 inches forecast because the highest values are currently supported by only 1 or 2 ensemble members. Still, those 8 to 10 inches amounts remain in the guidance. They have not been ruled out. This is the narrow space forecasters often have to navigate, balancing what is most likely against what remains possible if the atmosphere organizes in just the wrong way. That brings the drought to deluge part of the story into focus, and it is an important piece Calm Space has discussed before. In early May, during coverage of the worst drought in recorded history, the concern was not only that drought conditions would eventually break, but that what replaced them could create a different kind of hazard. Now that exchange appears to be arriving. The corridor that may receive 8 to 10 inches of rain is currently in extreme to exceptional drought. The ground there is not merely dry, it has become hardened, almost concrete-like. Soil in that condition does not readily take in water. Instead, it can shed rainfall, sending it rapidly into roads, channels, creeks, and low spots. That is why a flood risk after drought can be so deceptive. A landscape may look desperate for rain, yet when the rain comes too quickly, the land may be unable to accept it. The result could be a sudden transition from parched ground to dangerous runoff, with very little time between the first heavy downpour and the first flooded crossing. When a storm drops 3 inches of rain in a single hour on a county hardened by drought, the ground is no longer a sponge, it becomes a surface. Water sheets away almost immediately, finding creeks, bayous, storm drains, and underpasses before those systems have time to respond. That is the central concern now in the Houston area forecast discussion. Yesterday's rainfall has already saturated soils along the I-10 corridor, so any new rain today may convert into runoff more quickly than it normally would. The 0H guidance still points to localized rainfall maxima above 4 inches in the Houston metro, with the most likely bullseye near or south of E10. At the same time, PWAT values pushing into the region are above 2 inches, and rain rates are reaching the 3 to 4 inches per hour range. In practical terms, places like the Wallace Press Conference Center, the I-10 underpasses, and the bayou system may be placed under real-time stress during the late afternoon and evening. This is where a forecast stops being an abstract map and becomes a question of how fast water can move through a city. The San Bernard River and the Lavaca-Navidad River Basin also deserve attention, because both basins are being monitored for rises linked to upstream rainfall that has already occurred. Officially, the expectation for now is only isolated rises into action stage. But that assessment is based on the rain already on the ground. It does not yet account for what is expected to fall during the next 24 hours. If the HREF worst-case bullseye comes even close to verifying, those river basins could be telling a very different story by Sunday morning. Across Texas through Sunday, the broader image is a slow upper low edging northeast across the state, lingering long enough to support multiple corridors of training severe convection. Those corridors are capable of producing 3 to 4 inches per hour rainfall rates within an anomalously moist air mass at the 95th percentile for the date, all falling on drought-hardened ground that has little room left to receive it. The official flood watch shows 6 to 8 inches in 24 hours over the North Texas bullseye, while the more aggressive HREF guidance raises that to 8 to 10. The Panhandle is already encountering the leading edge. The Houston Metro lies inside the soaked soil amplification corridor. The river basins are under watch. In an event like this, if you are in the bullseye, road water is not something to test. You do not drive into it. Flash flooding over drought-hardened ground can develop with dangerous speed, and the water may rise faster than a driver can judge. Turn around. Do not drown. That phrase is repeated because the risk behind it is real. And with a slow-moving upper low, the atmosphere often keeps going after the first wave appears to be finished. Saturday is the Texas chapter, but by Sunday that same upper low is expected to lift farther northeast. The same training corridor mechanism is then forecast to organize across Missouri and Arkansas and eastern Kansas and eastern Oklahoma, a pattern we will return to in Part 6. For the moment, the Texas message is direct. Tonight's threat is substantial, the bullseye numbers are extreme, and the infrastructure along the corridor is about to be tested. If you are in the E35 corridor, anywhere near and west of E35 and north of E20, or along the E10 corridor in Houston, you should not be on the road after sundown unless travel is truly necessary. Keep your phone close, know which river, creek, or bayou is nearest your home, and think through where you would go if it began to rise. This is the second of 6 events firing tonight. A slow-moving upper low, an 8 to 10 inches bullseye, drought-cracked ground, and the same large-scale pattern behind the Ohio Valley severe weather we just traced. The atmospheric configuration is similar, but the hazard is different. The third event is more unexpected for many viewers, because southern Manitoba is not usually the first place people imagine when they think of tornado country. For one evening, that perception may need to shift. Part 4 takes us to Saturday evening over the Canadian prairie. There is one number used by operational severe weather forecasters that is worth understanding: the Significant Tornado Parameter, or STP. It is a composite index, meaning it folds several atmospheric ingredients into one value, including storm relative helicity, lifted condensation level height, convective available potential energy, and deep layer wind shear. The purpose is not to guarantee a tornado, but to offer a broad sense of how supportive the environment may be for significant tornado formation. In the scientific literature, significant tornadoes are EF2 or stronger. The scale begins near 0 and can reach 10 or higher at the most extreme end. When STP sits between 0 and 1, tornadoes may be possible, but the environment is not especially favorable. Between 1 and 3, the setup becomes more supportive, and some tornadoes may be strong. Once the value rises above 4, forecasters begin looking at an environment that can produce significant tornadoes if storms manage to form. The high-resolution rapid refresh model output for Saturday evening, roughly between 8 and 9:00 local time, places the STP at 5.2 over an area east of Regina and west of Brandon, spanning southern Saskatchewan and southern Manitoba. For early June in that region, that is an unusually notable value. Multiple operational sources have highlighted it independently. One forecaster described it as the sort of number not seen every day, while another identified it as the highest single-cell tornado risk on the continent for the day. The meteorological setup behind that STP reading also fits what forecasters would expect if 1 or 2, or possibly more, large tornadoes were to develop in that corridor on Saturday evening. The next question is what, exactly, is assembling that environment? The same broad upper-level trough helping drive both the Ohio Valley severe weather and the Texas flash flood threat is also shaping the synoptic pattern over the Canadian prairie. Near the Montana-North Dakota border, a deepening surface low is expected to initiate a round of late afternoon supercells on the US side. But the surface setup does not stop at the border. It extends northward, with the cold front, the dry line boundary, and the warm sector all arranging themselves across the southern Canadian prairie. In that alignment, the prairie sky may briefly hold the same kind of focused ingredients that severe weather forecasters watch with particular care. By Saturday afternoon, the warm sector spread across southern Manitoba and southern Saskatchewan is expected to feel unusually primed, with temperatures in the upper 70s and low 80s Fahrenheit, and dew points rising into the upper 60s as Gulf of Mexico moisture is carried northward on the low-level jet. That supplies the instability, the fuel that storms need before they can become dangerous. But the more troubling part of this setup lies in the wind field. Through the evening, the low-level jet is forecast to intensify as the surface low deepens, while the mid-level winds back, turning more southerly with height and creating the kind of directional wind shear that can help supercells rotate. The lifted condensation level across the warm sector is also expected to stay relatively low, within a range that can favor tornado formation. At the same time, storm relative helicity values, a measure of low-level rotational potential, are forecast to rise into territory supportive of significant tornadoes. When these ingredients are considered together, they produce an STP reading of 5.2, a value that is highly unusual for this region in early June. That kind of number does not appear casually. It usually points to a very particular alignment in the atmosphere. In this case, the key pieces are the placement of the upper trough, the strength of the surface low, and the position of the warm sector. Those same features are also helping generate severe weather in 5 other parts of the continent at the same time, which is why this Canadian prairie risk cannot be viewed in isolation. The most concerning window is expected to begin around 0 inches the evening local time and last until about midnight, with the highest STP values occurring near the beginning of that 8 to 9 evening period. What remains uncertain is storm mode, and that single question may decide how far the tornado threat actually goes. If storms stay separated as discrete supercells, southern Saskatchewan and southern Manitoba could see at least one, and perhaps more than one, large tornado Saturday evening. If they consolidate into linear segments before tornado initiation, the main hazards would more likely shift toward damaging wind and hail, with a lower tornado risk. The high-resolution rapid refresh is currently showing a discrete supercell signal in its hourly output. That is not a guarantee, because models can miss the details, but it is the best available guidance for resolving the storm mode question at the leading edge of the forecast, and its signal favors discrete supercells. The communities in the highest threat zone are not as large as the population centers discussed earlier in the Ohio Valley. Regina has a population somewhere around 230,000. Brandon is around 50,000, and the risk extends toward York, the communities along the Yellowhead Highway and Highway 1 across the southern Canadian prairie. Even though fewer people live in these areas compared with the Ohio Valley, the risk to any one person may be higher because the environment supports stronger tornado potential than the brief spin-ups indicated by the SPC for eastern Ohio. It is worth pausing over that contrast, because it helps clarify why this part of the forecast matters. For many viewers, especially those in the United States, tornado risk is mentally tied to a familiar seasonal map, but tonight's atmosphere may not follow the pattern people expect. In the United States, tornado climatology reaches its strongest intensity across the Central Plains and the Mid-South, with Oklahoma, Kansas, Nebraska, Iowa, and Missouri carrying major risk during April and May, followed by a shift eastward toward Mississippi, Alabama, and Tennessee in late autumn and winter. Canadian tornado climatology is different. Its peak arrives in midsummer, with most tornado days clustered in late June, July, and August across the southern prairie provinces. Today sits near the front edge of that climatological window. Early June, large tornadoes in southern Saskatchewan and southern Manitoba have happened before, but they are not the seasonal center of gravity. The 2007 Elie F5 occurred on the 22nd of June. The 2018 Alonzo F4 occurred on the 3rd of August. The 2021 Scarth tornado occurred on the 7th of August. Those dates show that the later summer peak is real, while also reminding us that damaging events are not confined to the heart of the season. When early June produces a larger Canadian prairie tornado threat, it often involves a setup much like the one being monitored now: a strong synoptic scale trough, a strong surface low, a warm and moist sector, and strong wind shear arranged together. If you live in southern Saskatchewan or southern Manitoba and are watching Calm Space, the practical message is the same one given for the Ohio Valley. Monitor Environment Canada warnings tonight. Make sure you have a way to reach shelter quickly. If a tornado warning is issued, go immediately to a basement or to an interior room on the lowest floor of your building. Do not let the later climatological peak create a false sense of safety tonight. The environment is loaded and the timing matters. From a broader perspective, this Canadian portion of the story may seem, to an American audience, like a secondary detail. It is not. It belongs in the same discussion because the Saskatchewan-Manitoba tornado threat is being driven by the same upper trough responsible for the Ohio Valley severe weather and the Texas flash flood threat. The same atmospheric pattern producing 8 to 10 inches raining corridors over central Texas this evening is also producing STP 5.2 tornado environments over the Canadian prairie at the same time. That connection is not incidental, it is the pattern itself. This is the larger shape to keep in mind as the forecast continues. 5 of 6 events have not even begun yet, and already 3 high-impact severe weather episodes have been identified in 3 different regions of the continent, all developing at the same time and all tied to the same upstream wave configuration. The unusual part is not simply one event in isolation, it is the simultaneous nature of all 3, forced by the same broader atmospheric structure. That is the structural anomaly, and it is what makes this week stand apart. Now the view needs to widen, because everything just described is only the opening portion of the 9-6-hour window from Saturday into early Sunday morning. Another part of the story has already been unfolding for most of a week, quiet enough that it may have faded into the background. The river floods in Missouri, Kansas, and Nebraska did not begin with today's data. They began a week ago, and what is expected on Tuesday is likely to make them worse. Before we move into Sunday, and before the Tuesday-Wednesday reload enters the picture, we need to pause over the rivers that have not yet had a chance to fall. This is part 5, the rivers that never stopped rising. Across the Central Plains, the signal has been clear for days. The Missouri River system is already in flood, it remains in flood, and the guidance keeps it there through Tuesday, with conditions likely lingering beyond that point. That distinction matters. The river flooding across this region is not being driven by the same immediate trigger as tonight's Texas flash flood. Instead, it is the lingering imprint of an earlier round within the same broad atmospheric pattern now producing tonight's compound event. In a calm map room, this is where the story begins to widen. One part of the sky delivers sudden water, while another part leaves the landscape still trying to drain. The active river warnings show how much water is already in motion. Along the Missouri River at Miami, Missouri, affecting Salin, Chariton, and Carroll counties, a flood warning remains in effect until late Wednesday evening, with minor flooding forecast. At 18 feet, low rural ground outside the levees begins to take on water. Downstream and nearby, the Missouri River at Waverly is under a flood warning until Tuesday afternoon, while the Missouri River at Napoleon, affecting Ray, Lafayette, and Jackson counties remains under a flood warning until early Tuesday morning, with minor flooding already happening and additional minor flooding forecast. The Grand River system is also carrying a heavy load near Sumner, affecting Chariton, Lynn, Carroll, and Livingston counties. A flood warning is in place, with moderate flooding occurring and moderate flooding forecast through late Tuesday evening. Near Chillicothe, the Grand River remains in a flood warning until early Monday afternoon. Near Gallatin, the warning continues until late Monday morning. Near Pattonsburg, affecting Daviess and Gentry counties, moderate flooding is occurring and moderate flooding is forecast until late Sunday evening. At 25 feet on the Pattonsburg gauge, low-lying farmland starts to flood. At 30 feet, nearly all agricultural land along the river is covered. The Platte River, near Platte City, Missouri, was upgraded overnight from minor severity to moderate severity, and forecast moderate flooding is expected to continue through late Wednesday evening. The Platte River at Sharp Station and the Platte River near Agency are both also under flood warnings, with moderate flooding. The 102 River at Rosendale, in Andrew and Buchanan counties, has likewise been raised from minor to moderate, while the 102 River at Emville remains under a flood warning with minor flooding. Farther north and west, the Big Sioux River near Bruce and near Esterlane in eastern South Dakota is under a flood warning until further notice, with minor flooding occurring. The Big Blue River near Blue Rapids in Marshall County, Kansas is under a flood warning. Salt Creek near Ada in Ottawa County, Kansas is under a flood warning. Turkey Creek near DeWitt in Gage and Salin counties, Nebraska is under a flood warning as well. Put together, that is 18 separate river flood warnings, with several upgraded to moderate flooding during the last 24 hours, stretching across Missouri, Kansas, Nebraska, and South Dakota. The amount of water moving through this system is immense. Its downstream effects are already showing up across agricultural land, while bridges, rural roads, and levees are being tested in real time. And all of this is happening before the incoming Tuesday surface low has even arrived. This is the quiet part of flooding that often slips out of view. The river remembers what the headline has already left behind. The broader point is easy to miss, because news attention usually shifts once floodwater is no longer the most immediate story of the day. The Missouri River, the Grand, and the Platte remain in flood mode because rainfall fell over the Central Plains during the past several days. That rain came out of the same atmospheric setup that has been producing severe weather across the Midwest all spring. It is the same pattern discussed in the bomb cyclone video, the atmosphere lock floods video, and the drought to deluge video. And now, that same pattern is involved in tonight's compound event. Operationally, the consequence is straightforward but serious. The rivers of the Central Plains are set to receive the Tuesday and Wednesday reload while they are still carrying floodwater from the previous round. The Tuesday surface low, described by the WPC as an unseasonably strong low-pressure system for June, is expected to pull a cold front across the northern plains and help ignite Tuesday and Wednesday's severe weather. That same setup will send additional rainfall into upstream catchments that have not yet finished draining. The rivers are not expected to crest, empty out, and reset before the next water arrives. Instead, they are likely to crest while the next round begins pushing more water into the channel system. At the Pattonsburg gauge on the Grand River, moderate flooding is forecast until late Sunday evening. If Tuesday's rainfall is placed on top of that, flood mode does not end, it stretches forward. The same logic applies to the Sharp Station gauge on the Platte. It also applies to the Miami gauge on the Missouri itself, where minor flooding is forecast through late Wednesday evening, even before the Tuesday rain is added. This is where a river forecast becomes more than a list of stages and warnings. It becomes a measure of whether the atmosphere is giving the land any time to recover. So the key lesson from the river discussion is this. The Central Plains River flooding should not be treated as a separate story from tonight's compound severe weather. It is the same pattern speaking through another pathway, on another clock. The configuration that is now helping fire severe weather in the Ohio Valley and the Texas flash flood is also the configuration that has been feeding rainfall into the Central Plains during the past week. A river system acts like the accumulated memory of that pattern. As long as the pattern remains locked in place, it keeps adding new entries to that memory. The longer the lock holds, the longer the rivers remain loaded. That is why the next phase matters. As we move through Sunday and into next week, we are really watching the next several days of the same atmospheric architecture. Whether it breaks or holds may determine what happens not only to the rivers, but also to the heat dome, to western fire weather, and to the broader chain of impacts connected to this setup. The next 48 hours of weather are shaped by the pattern. The next 10 days of consequence depend on whether that pattern locks in or finally releases. In that sense, Sunday is not just another forecast day. It is a question posed to the entire system. Let's look at what the pattern is doing on Sunday. First, though, it is worth lingering for a moment on what makes Missouri River and Grand River flooding structurally different from the kind of flash flood many people picture first. A flash flood often behaves like a concentrated point source event. A thunderstorm drops 3 inches of rain on a waterhead in an hour. That water rushes into a creek, and the creek crests within a few hours. River flooding on these larger systems unfolds differently. It is slower, broader, and more cumulative because it gathers water from multiple upstream areas and carries the delayed response downstream over time. That difference may sound subtle, but it changes the entire nature of the threat. A flash flood can be sudden and violent. A river flood can be persistent, layered, and difficult to unwind once the basin is already saturated with runoff. A flash flood often behaves like a brief surge through a narrow moment in time. The crest passes downstream, and the immediate danger either strikes a place or it does not. Within about 12 hours, that first threat can be finished. River flooding works on a slower clock. It is the gathered result of rainfall spread across a wide catchment and stretched over a longer period, a kind of accumulated signal moving through the landscape. The Missouri River at Napoleon is not in flood simply because Napoleon received heavy rain. It is responding because rain fell across the entire upper Missouri basin over the past 2 weeks, and that basin is now gradually draining downstream. The Grand River at Pattenberg is in moderate flooding for the same broad reason. Water collected over an enormous area, and the rising stage on the gauge is the downstream expression of 2 weeks of upstream weather. That distinction matters because it changes how we should read the river. First, flooding can continue well after the sky has cleared, since the catchment is still releasing water. The crest at Pattonsburg is forecast for late Sunday evening, the crest at Napoleon for early Tuesday morning, and the crest at Miami for late Wednesday evening. In other words, some of the water that will define the next crest has not reached those locations yet. It is still upstream, moving slowly through the catchment. So the river can continue to rise even on days when no local rain falls in the immediate watershed. Second, Tuesday's incoming surface low will arrive over a river system that is already burdened. Its rainfall will not behave like one isolated burst. It is expected to be the sort of multi-day frontal passage rainfall that spreads across the same upstream catchments. Another 2 to 3 inches of rain over the upper basin, distributed across 2 days and falling onto basins already at moderate flooding stages, could act as secondary loading. That kind of addition may lengthen crest durations and push gauges beyond what the current forecast is considering. Right now, the forecast does not include Tuesday's rainfall. It will be revised as Tuesday draws closer. For anyone along the lower Missouri, the lower Grand, or the lower Platte, those updates deserve careful attention. This is the slow motion part of the weather story. where the atmosphere leaves a delayed imprint in the rivers. There is also a quieter feature in this flood picture, the levee systems, which often do not appear clearly in headline alerts. Along the Missouri River, the levee network is not a single uniform structure. It is a patchwork of federal levees, state levees, and private agricultural levees, all built to different specifications and with different engineering tolerances. Some are designed around a 100-year flood, others around a 50-year flood, and others around a 20-year flood. Some are simply earthen BMS with no formal design at all. Current Missouri River system stages remain below the design failure thresholds for most of the federal levee system, but that does not mean every barrier in the landscape has the same margin. They are not below the design failure thresholds for all private agricultural levees. During the past 2 weeks, levee breaches in the agricultural levee system have been documented on the Grand River and on the Lower Platte. Most have been minor, and most have not become headline stories. Even so, they have added to the cumulative flood inundation footprint and help explain why the present forecast points towards sustained flood stage conditions through Wednesday, rather than a rapid fall. Put another way, the river system is holding the memory of the pattern. The gauge readings across the Missouri Basin are the remaining record of the last 2 weeks of weather. And Tuesday's incoming surface low is expected to add another layer to that record. As long as the pattern stays locked in place, it keeps writing itself into the rivers. Only when the pattern unlocks do the rivers begin to unload. Until then, they remain charged, carrying the past downstream. This is the moment to speak directly to anyone living in the counties currently under flood stage concerns. The flood warnings in effect are not abstract, they are based on real conditions. Forecast crest values are calculated from rainfall that has already fallen, not from every possible addition ahead. If you are in a low-lying area near a river or downstream of a levee with any history of breaching, the most important guidance will come through local emergency management communications. The federal, state, local floodplain management framework exists for this type of event, and the practical instructions will come from the local office responsible for your area. Calm space is not a replacement for those local messages. Its role here is to place the local forecasts inside the broader atmospheric pattern, so the behavior of the rivers becomes easier to understand. In this case, that larger picture is clear enough to be taken seriously. The river floods in Missouri and Kansas and Nebraska are not finished, and they are not likely to be finished by Tuesday. Tuesday's surface low is expected to load them again. The same pattern producing the compound severe weather event we have been following is also feeding the river response. It has not broken yet. It reloads on Tuesday. If the European model verifies, the same setup could produce a Wednesday severe weather day that the SPC has not yet placed in its highest categories, though it is watching closely. That is why the river floods belong in this discussion, even for viewers not directly affected by the water. They are the integrated memory of the pattern, and the pattern is what we are tracking. In a calm sky, it can be easy to forget that the basin is still moving. Part 6, Sunday. The pattern reloads. Just before 1 inch the morning Central Time, the Storm Prediction Center released its Day 2 convective outlook, identifying a slight risk corridor across the northern plains for Sunday. Within that corridor, the stated hazards are large to very large hail, severe wind gusts, and a possible tornado or two. The outlook narrative centers on a vorticity maximum, with related mid-level and upper-level jet streaks embedded near the base of broader-scale troughing, accelerating northeast through the northern high plains. Ahead of the prefrontal trough over the western Dakotas, a hot, deeply mixed boundary layer is expected to form. Steep low-level and mid-level lapse rates then support an axis of moderate to strong instability. Storms emerging from Montana and Wyoming are expected to mature within a strongly sheared environment, a setup that favors supercells capable of large hail. Later in the evening, Some tornado threat may develop across portions of north-central North Dakota, where strengthening low-level shear could overlap with a more moist LCL boundary layer. The atmosphere, in this view, is not resetting, it is reorganizing. Sunday may become another chapter in the same larger sequence, one more sign that the pattern has not yet released its hold. In plain terms, Sunday's severe weather picture over the northern plains resembles Saturday's setup over the Canadian prairies, only nudged a little farther south and carrying a different intensity balance. The environment is not showing the same significant tornado parameter of 5.2, it is more restrained than that. Even so, it remains capable of supporting supercells with large to very large hail. The central question is still storm mode. And that detail matters because the shape of the storms often changes the hazard. If storms remain discrete, the main concerns become hail and a few isolated tornadoes. If they consolidate into a line, damaging wind becomes the more prominent threat. At this stage, the forecast favors a blended outcome rather than one clean solution. Farther east, the Day 2 outlook also places a second slight risk from central Virginia into the Chesapeake Bay area. There, the setup is built around daytime heating and dew points in the 60s, allowing a moderately unstable air mass to develop by afternoon. Isolated to widely scattered thunderstorms may form through the afternoon, with locally damaging wind gusts as the leading concern into the early evening. In a broader sense, this is the mid-Atlantic echo of Saturday night's Ohio Valley event, translated east and south as the upper trough advances. A smaller tornado signal also appears over eastern Oklahoma and western Arkansas, where lift is tied to a vorticity maximum moving through the base of the troughing. The window is Sunday afternoon into Sunday evening, especially from 5 to 10 inches the evening local time, when a couple of supercells could form near the Fort Smith corridor and perhaps extend southeast of Tulsa. The significant tornado parameter in that zone is only between 0 and 1, so the more realistic concern would be brief spin-up tornadoes rather than long-track significant tornadoes. Alongside the severe threat, the flash flood concern shifts east on Sunday as the upper low itself moves eastward. The same training corridor mechanism affecting Texas from Saturday into Sunday morning is expected to organize across Missouri, Arkansas, eastern Kansas, and eastern Oklahoma through Sunday. The flooding rain risk is a level 2 of 4. Its fuel is a 40 miles per hour low-level jet carrying moist air into the corridor, sustaining heavy rainfall over the same general zone. If you are going to Busch Stadium for the Cardinals game on Sunday afternoon, the practical message is simple. Take an umbrella and remain alert for street flooding near the ballpark. Stepping back, Sunday is less a new pattern than a relocated one. The atmosphere is repeating many of Saturday's behaviors, but over different terrain. The flash flood axis shifts from central Texas toward eastern Kansas. The severe weather corridor that affected the Ohio Valley moves into the mid-Atlantic. A fresh, severe weather zone opens over the northern plains. Meanwhile, the Canadian prairie tornado risk remains close to where it was Saturday, only slightly displaced. The pattern does not truly stop. It turns, and that rotation is what carries the risk from one region to the next. Then Monday arrives. And Monday stands out because the atmosphere appears to pause, at least briefly. Across most of the country, the severe weather threat is lower than it is on Saturday or Sunday. Still, lower does not mean absent. Illinois could see some severe storms during the daytime, with isolated large hail and damaging wind gusts. Kentucky or Tennessee may carry a low tornado risk. Across Minnesota, a couple of supercells are possible between 4 and 10 inches the evening local time, mainly producing large hail and damaging winds. Nebraska, Kansas, and Colorado may also have a stormy afternoon and evening, with a cluster of thunderstorms moving in from the west and bringing mostly a damaging wind threat. The storm mode there looks mainly clustered, though a few discrete supercells could develop ahead of the clusters. If that happens, a strong tornado cannot be ruled out, but the probability appears fairly low right now. So Monday looks calmer than the 2 days before it. It may be the breath the pattern takes before it reloads, because Tuesday and Wednesday are the part of the week that the operational severe weather community is watching most closely. Before moving into that next chapter, though, it is worth looking behind the troughs. The western states have been waiting for their side of the story since Saturday morning, and the heat dome building behind the sequence we have been following may become the feature with the longest after effect. Behind the troughs come the heat dome and the fire weather risk. While those troughs rotate through the eastern half of the country, a broad upper-level ridge over the southwestern United States is behaving exactly as ridges often do. It suppresses convection. It keeps the air mass beneath it dry. It pushes surface temperatures higher, and for this particular week, most importantly, it strengthens the surface wind gradient enough to create critical fire weather across 6 western states at the same time. This is the quieter side of the same atmospheric story, but it may be no less important. As of 1509 UTC on June 6th, the western states have 21 active red flag warnings and 16 fire weather watches in effect simultaneously. In Wyoming, the red flag warning, issued by the Riverton office and active until 8:00 inches. The evening mountain daylight time covers Norona County in central Wyoming. Conditions there include southwest winds of 15 to 25 miles per hour, gusts up to 35 miles per hour, and humidity as low as 7%. Across the Nevada and Arizona Lake Mead corridor, the red flag warning from the Las Vegas office remains active until 11:00 inches the evening Pacific Daylight Time. It covers the Spring Mountains, the Sheep Range, the Clark and southwestern Lincoln County deserts, and Arizona's Northwest Plateau, with southwest winds of 20 to 25 miles per hour, gusts up to 40 miles per hour, and humidity from 5 to 15%. On the Colorado Plains, the Denver office has issued a red flag warning active until 7 inches the evening for Northeast Weld, Central and South Weld, Morgan, Central and East Adams, and Arapjo and Logan counties. Southeast winds there are expected at 15 to 25 miles per hour, with gusts up to 30 miles per hour, and relative humidity as low as 14%. Farther west, the Nevada Eastern Counties red flag warning, issued by the Elko office, is active until 11:00 inches the evening Pacific Daylight Time. That warning includes southeastern Humboldt and northern Lander, White Pine and northeast Nye, northern Nye, central Nevada, Toyaba, Humboldt County, Quinn, and the western Elko County area. Sustained southwest winds near 20 miles per hour may gust near 35 miles per hour, while minimum relative humidity values fall as low as 9%. Taken together, this is the near-term snapshot for the next 24 hours. After Saturday, the signal does not ease, it becomes more concerning. The Goodland Hazardous Weather Outlook, covering the tri-state region of southwest Nebraska, northwest Kansas, and east central Colorado, points to the possibility of critical fire weather in the middle of next week, with a 30% chance that those conditions persist for several hours. If fires begin under that setup, they may expand quickly and become difficult to control. Farther west, the Denver AFD expects widespread critical fire weather conditions in fuel-prone areas by Tuesday and Wednesday. The Las Vegas Fire Weather Watch continues from Monday morning into Tuesday evening, while the Pocatello Fire Weather Watch for the Twin Falls area remains in effect through Sunday evening because of gusty winds and low relative humidity. Taken together, this is the second major pattern signature of the week across the West. The same broad upper ridge building the heat dome over the central and eastern United States is also tightening the wind gradient along its western side, and that gradient is helping create critical fire weather across the Mountain West. It is one atmospheric arrangement, producing more than one result. On the eastern side of the trough, the pattern favors severe convection. On the western side of the ridge, it favors fire danger. In both cases, the underlying driver is the same upstream wave configuration. That connection matters because it reminds us that heat, storms, flooding, and fire weather may not be separate stories at all, but different faces of the same larger pattern. From there, the focus turns to the heat dome, because this becomes the main feature for the second half of next week, and the piece that links the near-term hazards to the longer-running consequences. The Weather Prediction Center's extended forecast discussion, released at 4 inches the morning Eastern Time today, states the point directly. A significant heat wave is expected to build over a large portion of the central to eastern United States from mid to late next week. It is described as the first significant heat wave of the summer. The larger ridge is expected to support broad zones of above normal temperatures and heat indices as the heat wave establishes itself over the central United States Tuesday and Wednesday, then shifts and grows into the eastern United States later in the week. The specific numbers give that broad forecast some weight. Denver could approach 100 degrees F on Tuesday, while the standing Denver record for that date is 98 degrees set in 1918. That means Tuesday at Denver, Stapleton may come close to a daily record that has been in place since the Wilson administration. In South Florida, heat indices for the Gulf Coast rise into the low to mid 100 seconds on Sunday, with the Miami AFD noting that precipitable water values over Florida are dropping into the 1.1 to 1.4 inches range, near the lowest end for early June. In Wisconsin, the Milwaukee and Sullivan office is flagging the possibility of heat advisory conditions on Wednesday, Thursday, and Friday. And in North Texas, after the rainfall ends, heat index values near or above 100 degrees are expected to return during the post-flood week. This is where the wet bulb framework becomes important again, and it is worth pausing on why. The earlier wet bulb discussion from Calm Space is the right lens for this kind of heat dome, not only because it affects people, but because it also helps describe stress on infrastructure. Wet bulb temperature accounts for humidity as well as heat. Very hot air with low humidity can still allow sweat to work more effectively, but a high wet bulb temperature is a different and more dangerous category. The theoretical 35 degrees C wet bulb limit proposed by Sherwood and Huber in their 2010 PNAS paper is not the only threshold that matters. Empirical work by Vicelio and his collaborators in the Penn State heat chambers found that, for healthy young adults, the actual critical wet bulb temperature is closer to 31 degrees C. The research also suggests older adults have a lower tolerance still. That framework helps explain why heat-related casualties rise during long-duration heat waves when humidity is high. It was the central subject of the May United Kingdom heatwave video earlier this week, and it becomes relevant again as the central and eastern United States heatwave begins to take hold. To be clear, the eastern half of the United States is not expected to reach a 31 wet bulb during this event. That is the honest forecast. The point is not that catastrophe is imminent. Rather, the scale of the heat is large enough that wet bulb thinking becomes the appropriate way to evaluate risk. The operational hazards line up with what the framework is meant to describe. And the strain on infrastructure is also the kind of strain that framework anticipates. Next week's heat wave is the type of event that this framework suggests may occur more often and with greater intensity against a warming background climate. That is the connective thread between this week's compound event, the May United Kingdom heatwave discussion, the Pacific heatwave video from a couple of weeks ago, and the earlier videos before them. For the structure of this forecast, the most important point is that the heat dome is not isolated from the rest of the week. It is being produced by the same broader pattern already responsible for the other hazards. The same expansive upper-level ridge that is helping feed instability across the plains through moisture and instability profiles is also suppressing convection across the desert southwest. At the same time, that ridge is driving the wind gradient along its western flank, where the critical fire weather is developing. It is also the ridge that will trap heat over the central and eastern United States by midweek. And it is the same ridge expected to prolong Central Plains river flooding by helping feed Tuesday's incoming surface low. One pattern, four consequences, unfolding during the same week. That brings the forecast toward Tuesday and Wednesday. Tuesday is when the pattern reloads in its most dangerous mode, while Wednesday is when multimodal convergence becomes the piece drawing the closest attention from the operational severe weather community. Before moving into that, though, it is useful to slow down and look more carefully at the wind gradient mechanism on the western side of the ridge. Fire weather is often reduced to a simple formula of low humidity plus strong winds, but in this case that formula is being shaped by the same upstream structure behind the rest of the event. When a strong ridge settles over the desert southwest, air beneath it sinks. As that air subsides, it warms adiabatically, and that warming dries it out. The vertical profile below the ridge then takes on the form of a deep, dry layer sitting above a comparatively shallow surface boundary layer. In quiet language, that is the architecture behind the hazard. Not just dry air, not just wind, but a larger atmospheric design arranging the ingredients in place. Near the ground, the atmosphere has a working layer of its own, the surface boundary layer, where the surface winds are felt most directly. Those winds are not random. Their speed is controlled by the pressure gradient at the surface, and that gradient depends on how the larger synoptic scale features are arranged. At the moment, the upstream pattern is shaping the pressure field in a way that places higher pressure to the south and lower pressure to the north, with a sharp gradient stretched across the mountain west. When that gradient tightens, the wind responds. It is a simple connection, but in weather, simple connections can have far-reaching consequences. Strong winds moving through a deep, dry boundary layer over vegetation that has been under weeks of sun create the kind of fire weather setup now appearing in the alerts. So the cause does not stop at the local wind map. It reaches back into the configuration of the upstream wave pattern. The same wave train helping produce severe weather in the Ohio Valley is also setting the southwestern ridge in place. That ridge then shapes the wind gradient along its western side, and that gradient helps generate fire weather conditions across 6 states. This is why the fire weather threat belongs in the same discussion as the severe weather threat. It may look like a different hazard, but it is not an isolated atmospheric story. It is the same broad pattern expressing itself in another form. The upstream forcing is shared, while the downstream impacts vary by region. In the QR framework, that relationship becomes clearer. Fire weather is the dry side expression of the wave train. Severe storms are the wet side expression. River flooding is the accumulated memory expression. The heat dome is the ridge expression. The Saskatchewan tornado is the northeastern extension of the warm sector. And the Texas cutoff low is the cutoff low expression. 6 modes, 1 pattern, 1 mechanism. That kind of unity is easy to miss when the hazards are spread across a continent. Yet it may be the key to understanding why so many alerts can unfold at once. There is also another layer to the heat dome question, because the wet bulb framework mentioned earlier is the one that matters for human heat risk. But the operational effects do not end with mortality. Infrastructure stress is quieter, less dramatic in headlines, and often noticed only when something fails, yet it matters across the longer arc of an event. The climate central work discussed earlier this week by CalmSpace, in connection with the May United Kingdom heatwave, documented a 60% increase in US heat season power outages over the past decade. The pathway is not complicated. High temperatures place stress on transformer infrastructure. Transformer oil warms, and as the equipment heats, the transformers derate, meaning they can carry less load than their nameplate capacity under hotter conditions. At the same time, demand rises because air conditioning use increases. Those two pressures meet in the same system: lower effective capacity and higher load. Under those conditions, transformer failures become more likely than they would be in cooler weather. Local outages can then spread stress to nearby equipment, because the remaining transformers must carry more of the burden, and that added load can produce further failures. The first major heat wave of the summer next week is not expected to collapse the grid. The system is stronger than that. But it does represent the kind of recurring summer stress test that power infrastructure already faces, and one it may face more often as heat events become more frequent and more intense. Texas is especially important in this discussion because its grid has its own interconnection and is not directly tied to the eastern interconnection. That makes it more exposed to compound stress events like the sequence expected after the Texas flash flood, followed by the arrival of the Texas heat dome. Grid operators will be watching carefully. This is not only about next week. The broader point is that the infrastructure stress test returns every summer. As background warming continues, that test is expected to occur more often and at higher intensity. The coming decade is likely to include more weeks of this kind. Transformer failure rates are expected to rise. Summer outage frequency is expected to rise, and the combined consequences will be real. The mechanism has already been documented. In a calm forecast map, this may appear as just another dome of heat, but beneath it sits a network of physical systems being asked to operate closer to their limits. Part 8 brings us to Tuesday and Wednesday, and to a phrase from the WPC extended forecast discussion released this morning that deserves a moment of attention. An unseasonably strong low-pressure system, especially for June. In operational language, that points to a synoptic scale surface low whose depth is notably below the climatological mean for the date on the calendar. Surface lows over the northern plains in June are not unusual in themselves. They occur, and they are part of the seasonal machinery that supports summer severe weather. What makes the incoming Tuesday system stand out is not its existence, but its magnitude. The central pressure is forecast to be lower than the June mean, and the forcing associated with it looks more like what might be expected from a late spring surface low than from one arriving in early summer. At this range, the multi-model guidance has a reasonably focused track. The surface low is forecast to move out of the northern high plains early Tuesday, shift eastward on Wednesday, and then consolidate in south-central Canada by early Thursday. Behind it, the cold front will act as the focus for convection. Ahead of it, the low is expected to organize plentiful moisture, instability, and shear. The essential ingredients behind the multi-day risk window already being highlighted by the SPC in its hazardous weather outlooks for the northern plains and the upper Midwest. Tuesday's corridor is broad, covering North Dakota, South Dakota, and western Minnesota. On this portion of the forecast, the European model and the GFS are in fair agreement. The dynamics support a severe weather day, with storm mode likely to include both supercells and linear convection. The hazards are large hail, damaging winds, and the possibility of a tornado or two. For Tuesday, the central uncertainty is timing. When convection begins relative to the daytime heating cycle will determine how much instability is available once storms initiate. A few hours can matter in this kind of setup, because the atmosphere may look very different depending on whether storms fire early or wait until peak heating has done more work. By Wednesday, the guidance begins to separate, and that separation is what the operational severe weather community is watching most closely. The GFS, the American Operational Global Model, is not especially aggressive for Wednesday. It does show severe weather across parts of the Midwest, especially Minnesota and Wisconsin, but it is not signaling a high-end event. The European model, on the other hand, is substantially more forceful. It depicts a stronger, low-level jet shifting east of Minneapolis into Wisconsin, a low-pressure system that becomes better organized and a much more favorable severe weather environment over Minnesota and Wisconsin on Wednesday afternoon and evening. That contrast matters because it changes the ceiling of the event. One solution suggests a meaningful but more restrained severe weather day. The other raises the possibility of a more organized and potentially more consequential setup. At this stage, the forecast question is not whether the atmosphere will be active, but how strongly the ingredients will align, and exactly where that alignment will be maximized. The European model is raising a more serious signal for Wednesday than the GFS. In one solution, the atmosphere over parts of Minnesota and Wisconsin could organize in a way that supports a tornado outbreak. In the other, the day looks closer to a more standard severe weather event. When these two major models separate this sharply, at a 3 to 5 day lead, forecasters often give more weight to the European model for large-scale precipitation and surface forcing, because its average skill score is generally stronger in that range. Here, that matters. The European model has been stronger with the low-level jet, stronger with the surface low placement, and stronger with the convective parameter space. If its solution verifies, Wednesday could become an outbreak day in portions of Minnesota and Wisconsin. If the GFS verifies instead, the setup may still be dangerous, but less exceptional. Confidence is not yet high enough to declare the outcome in either direction, though the European model currently carries the stronger trend. That distinction is important, because in forecasting, the difference between a possible environment and an actual event can be very small and very consequential. The phrase tornado outbreak also needs careful handling. In this context, the operational threshold is 6 or more confirmed tornadoes in one weather event. The European model is not saying that 6 tornadoes will occur. It is depicting an atmosphere where the combination of wind shear, instability, and storm mode could support that result if the forecast ingredients come together. Whether they do depends on many smaller details: where the warm sector is when storms begin, how the cold front is timed, how strong the cap remains, and how deep the moisture becomes. Any one of those factors could reduce the ceiling of the event. At the moment, none is clearly forecast to shut it down. So the risk is not a certainty, but it is present, and it deserves attention. The areas that should watch Wednesday most closely include central Minnesota, southern Minnesota, and Wisconsin, particularly the western half of Wisconsin. The I-94 corridor from Minneapolis to Eau Claire, and from Eau Claire toward Madison, is especially important in this forecast window. The key updates will come from the SPC outlook cycle between now and Wednesday. The Day 3 outlook arrives Sunday morning, the Day 2 outlook follows Monday morning, and the Day 1 outlook comes Tuesday morning. How those outlooks evolve, whether the risk is increased, held steady, or reduced, will be the operational signal for what forecasters increasingly expect. In a setup like this, the trend is often as meaningful as the category itself, because it shows whether the atmosphere is moving toward the higher-end solution or away from it. After Tuesday and Wednesday, the pattern may not immediately relax. A Thursday severe weather risk is also on the table, tied to the same larger system as the surface low consolidates over south-central Canada and the cold front pushes farther east. The European model suggests that the severe threat could extend into Thursday across a broad zone east of the upper Midwest, possibly reaching into the Ohio Valley and the Mid-Atlantic. The GFS is again less aggressive with this part of the forecast. For now, that makes the trend the thing to monitor rather than a fixed conclusion. Meanwhile, there is another consequence from Wednesday into Thursday. Rivers across the Central Plains may remain under pressure. Tuesday's surface low is expected to bring more rainfall into upstream catchments where the Missouri, Grand, and Platte are already flooding. The forecast does not call for one single high-impact rainfall event in the Central Plains during the Tuesday-Wednesday period. Instead, the concern is cumulative. Additional rain falling on an already saturated basin system can prolong flooding rather than allow it to recede. Sometimes the most important hazard is not the dramatic new peak, but the way a system refuses to recover. Beyond the atmosphere and the rivers, the sun is running its own parallel chapter. It is worth pausing on the space weather background, not because it drives the severe weather pattern, but because it adds to the unusual simultaneity of this week. There are 11 numbered active regions on the solar disk right now. The largest, region 4458, measures 240 millionth of solar surface area and is developing a weak delta signature in its magnetic configuration. Region 4462 is still increasing, with 9 spots. Region 4455, the source of the X-class flare on June 3rd, remains visible on the disk and still carries a 25% M-class flare probability for the next 24 hours, along with a 5% X-class probability. At 1340 UTC today, June 6th, a new M1.8 flare erupted from S22E24. A Type 2 radio emission began at 1347 UTC, indicating a coronal mass ejection with an estimated velocity of 838 kilometers per second. At 1344 UTC, a 10 centimeters radio burst peaked at 190 solar flux units. The greater than 2 Me electron flux at geosynchronous orbit is expected to climb to high levels today and stay high through Monday. Across the next 72 hours, the probability of M-class flares remains 50% each day. The solar activity does not directly control the surface severe weather pattern discussed here. The energy budget mismatch is 15 to 17 orders of magnitude, which means the idea that solar activity is somehow driving this extreme weather lacks a physical mechanism that can carry the claim. Still, the timing is real. The solar cycle 25 active region complex remains energized, while the surface pattern is producing a compound continental severe weather sequence. Same week, same broad map, but not the same engine. That is the careful line. The coincidence may be worth noticing, while the physics does not support turning it into causation. There is also the recent geomagnetic storm to place in this background. As covered in detail 3 days ago in the segment on the 3 violent solar blasts racing toward Earth, the M9, 3, M7, 7, and X1. Zero sequence from June 3rd produced yesterday's G2 geomagnetic storm. That G2 storm reached a peak KP of 6.33 at 1500 UTC on June 5th, and aurora was visible at high latitudes. The storm has now mostly faded, but energetic particle flux is expected to remain elevated through Monday. The active region complex is still capable of producing more activity, and another M-class or X-class flare from region 4455 or 4458 remains statistically possible. In that sense, the space weather setting resembles the heat dome as a parallel expression of an active week. Solar cycle 25 is in its high activity phase. The active region count is elevated, and the probability of significant flares is also elevated. None of this needs a coupling mechanism beyond timing. The shared timing is the notable feature, not a hidden connection. That is where the story turns toward part 9. We have now moved through all 6 events expected to fire within the next 96 hours, along with the river floods, the heat dome, the western fire weather, and the solar backdrop. What remains is the larger question. Why are so many hazards unfolding at the same time? The published science does offer an answer. It is not new, and it is not fringe. The clearest answer is the quasi-resonant amplification mechanism, and this is the point in the story that deserves the slowest, most careful attention. It is where a practical forecast begins to touch a much larger question. Are we simply watching a run of ordinary severe weather, or Are we seeing a familiar atmospheric pattern expressed in a way that a warming climate may make more common? Part 9 begins here, with the reason 6 separate storms can seem to speak in a single voice. Across the scientific literature, including peer-reviewed work in leading climate journals, researchers have described the very kind of compound, continent-scale severe weather setup we have been following. The framework is known as quasi-resonant amplification, often shortened to QRA. It has been discussed for more than a decade, and it is not a fringe idea or a new speculation. It is mature enough, and the physical process is understood well enough that it is used by operational severe weather forecasters, climate monitoring specialists, and long-range forecasting teams. In other words, this is not an obscure theory sitting far from the forecast desk. It is part of the working language of modern atmospheric science. To understand it, we can set aside some of the technical vocabulary and follow the motion of the atmosphere itself. The jet stream is a fast current of air flowing near the boundary between cold polar air and warm tropical air, circling the northern hemisphere at roughly the latitude of the United States and Canada. Its speed depends strongly on the temperature contrast between the equator and the pole. A sharper contrast helps drive a faster jet. A weaker contrast tends to produce a slower one. When that current is moving quickly, it usually behaves more like a straighter west-to-east highway with smaller bends, allowing weather systems to move through and move on. A cold front may cross a city in a day and be gone within 2, but when the jet stream slows, the pattern can become more wavy, with broad north-to-south swings, deep troughs dipping southward, and tall ridges extending northward. Those bends can drift slowly, and sometimes they barely move at all. A front trapped in such a sluggish pattern can linger over the same region for days, while a ridge caught in place can hold heat over one area for a week or 2. This is the important turn in the mechanism. The atmosphere does not merely produce weather. At times, it locks the stage on which that weather keeps repeating. The key idea in quasi-resonant amplification is that the jet stream waves can arrange themselves into a particular wave number pattern, with roughly 5 to 8 large waves distributed around the northern hemisphere. If those waves also become high amplitude, with pronounced troughs and ridges, and if their motion slows dramatically, the atmosphere enters the kind of state described by the QRA framework. The wave pattern holds. Regions beneath the same part of the wave remain exposed to the same broad atmospheric influence for days or even weeks. Troughs stay where troughs have been. Ridges hold where ridges have built. Under the troughs, the same general storm-supporting environment may recur day after day, while under the ridges, a different but equally persistent set of conditions may dominate. That is why widely separated extremes can unfold at the same time, without being random, isolated accidents. They may be different faces of one planetary scale wave pattern. Several published studies help anchor this idea. The 2020 Kornhuber paper in Nature Climate Change formalized the framework and showed that QRA events are associated with simultaneous high-impact extremes across separated regions of the Northern Hemisphere. The 2023 Kornhuber paper in Nature Communications extended the analysis to synchronized concurrent extremes, connecting QRA events with high-impact weather affecting multiple agricultural breadbaskets at once. The 2021 Hand paper in Water Resources Research identified low-phase speed Rossby wave packets as the dynamical signature of the kind of persistent extreme weather patterns that the QRA framework anticipates. These papers matter because they point to a common architecture behind events that, on the surface, may look disconnected. They suggest that the atmosphere can organize extremes across great distances through the shape and speed of its waves. So what does this have to do with the next 96 hours? It has to do with almost everything. The present upper-level pattern over North America has the signature of a QRA-style setup. A trough in the west, a ridge over the central United States, and another trough over the eastern United States. The waves are large in amplitude. Their phase speed is slow. The broader arrangement has been locked in place for much of a week. Each region, sitting beneath a different part of the wave train, is receiving the kind of weather that part of the pattern tends to deliver. The Ohio Valley, under the influence of the eastern trough, is dealing with severe convection. The central and eastern plains, beneath the ridge, are moving toward the heat wave. The desert southwest, positioned along the western flank of that ridge, is facing critical fire weather. The northern high plains, near the base of the western trough, are tied to the surface low and the Tuesday-Wednesday severe weather reload. The Canadian prairie, under the warm sector northeast extension of the wave train, carries the tornado threat. Meanwhile, the slow-moving upper low over Texas fits the cut-off low behavior that commonly appears when a strong wave pattern develops. It remains over the state because the larger wave train from which it separated is not moving quickly. Seen one by one, these are 6 events. Seen from above, they are one pattern. That distinction matters because it changes the question we ask. The issue is not simply whether the individual hazards are in the forecast. The forecasts already indicate that they are. The deeper question is whether the pattern producing them is the sort of pattern that a warming world may favor more often. This is where the Rantanen 2022 paper in Communications, Earth and Environment becomes relevant. That paper documented that the Arctic is warming at approximately 4 times the global mean rate. The reason this matters returns us to the temperature gradient principle at the beginning of the discussion. If the Arctic warms faster than the equatorial regions, the pole to equator temperature contrast weakens. A weaker contrast can slow the jet stream. A slower jet stream can form larger amplitude meanders. Those larger meanders are precisely the kind of configuration that the QRA framework links to simultaneous, geographically separated extremes. Put in simpler terms, Arctic warming weakens the driving contrast for the jet stream. A weaker jet may build broader waves. Broader waves can become stuck, and stuck waves can yield compound continental extreme events. The next 96 hours across North America may therefore be viewed as an operational expression of a pattern that the published science suggests could become more frequent as the Arctic continues to warm. Still, the wording has to remain careful. The framework is established, and the mechanism is used operationally, but assigning any single event directly to the background warming climate is a more difficult scientific judgment. The peer-reviewed record has not reached the level of confidence that operational meteorologists would need before saying that the exact compound event now developing across North America could not have occurred without the background warming already in place. That distinction matters. What the published science does support is a broader statement. Events of this kind, large-scale continental extremes, unfolding in combination over a period like the next 96 hours, have appeared more often across recent decades, and the same literature expects them to occur more often in the decades ahead. That expectation fits with the QR mechanism and with the wider setting of Arctic amplification. This is the careful version of the claim. The atmospheric pattern is present. The mechanism has been described in the literature. The framework points toward more episodes of this type. But formally assigning one particular event to one particular cause remains difficult. In climate science, the long-term pattern can be much easier to read than the single weather chapter happening in front of us. It is also important to hold the competing interpretation in view, because disciplined analysis should leave room for both readings until the evidence narrows the answer. The alternative is the null hypothesis, that the next 96 hours are simply one expression of natural climate variability. Weeks of compound severe weather do occur. The historical record contains them. The 2010 Milbury anniversary referenced earlier in this video is one example. The June 2010 record for compound severe weather days is comparable to the 2026 record so far. In 2011, the super outbreak season brought severe weather into multiple regions of the country at the same time. In 1936, the mega flood year produced simultaneous record river flooding across the central and eastern United States. In 1953, the tornado season generated compound severe events across both the plains and the south. So the past does not allow us to pretend that compound events are new. They are real features of the atmosphere. The deeper question is whether their frequency and strength are shifting. The published science says yes. The historical baseline data points in the same direction. Operational meteorology is increasingly working from that assumption. Even so, a single event can still stand alone as possibly random. That uncertainty is not a weakness. It is the honest scientific position. We may be watching the kind of outcome the framework anticipates, but one episode by itself does not prove the framework. The stronger evidence comes from the accumulated record over decades. Another part of the picture belongs in the same frame, because the larger Earth system context may be shaping the background on which this pattern is unfolding. The ENSO state right now is warm, neutral, and trending warmer. The official Oceanic Nino Index for March, April, and May of 2026 registered plus 0.48, which places it in the warm, neutral range. By comparison, the October, November, December value from 2025 was negative 0.55 in the cool, neutral range. Over 6 months, that implies a shift of approximately plus 1.03 degrees C. That is among the faster cool-to-warm ENO transitions in the modern instrumental record, comparable to the early stage of the 2014 to 2015 El Niño onset. The June 1st ECMWFC's 5 plume discussed in yesterday's video indicated a 51-member ensemble convergence toward plus 3 degrees C warming in the Nino 3.4 region by December of 2026. In the modern instrumental record, that would sit at the limit of what can be measured as the strongest El Niño, developing on a planet already 1.2 degrees warmer than the 1,876 baseline. In other words, the wider Earth system signal is building. And that same broad signal is connected to the kind of pattern-locked atmosphere described by the QR framework. A warming Arctic, a slowing jet stream, high-amplitude wave trains, a stuck pattern, and the resulting compound, continental severe weather. The signal is not isolated in one corner of the climate system. It is integrated across it. The 2026 hurricane season is being loaded by the same ENSO signal that is also loading the 2026 atmospheric pattern. Tropical storm Amanda in the East Pacific this week is the first sign of the season's tropical activity. The first major summer heat wave developing over the central and eastern United States next week is the first sign of the summer's continental heat dome activity. The ENSO warming, the QR pattern locking, the compound severe weather breaking out across the continent, and the river floods, still carrying the leftover imprint of the previous expression of that same pattern, all belong to one connected framework. That is what the science describes. That is what the next 96 hours are placing in front of us. As we move toward the end of this discussion, the important thing to keep is the structural question. The framework does not settle every answer for us. It helps us ask the question in the right way. There is also a second part of the QR framework to consider. Because the idea has been refined since the original Pikov work in 2013 and the original Kornhub work in 2017, and that refinement helps explain what may be visible this week. The 2020 Kornhub paper introduced the idea of zonal wave number 7 dominance. When the hemispheric wave train becomes stuck in a QR configuration, it often arranges itself into 7 roughly evenly spaced waves around the northern hemisphere mid-latitudes. This 7-wave structure is a specific stationary pattern. Once the hemisphere settles into it, troughs and ridges can hold their positions with unusual persistence, leaving the same regions beneath the same wave components for extended periods. That kind of atmospheric stillness is why the concept matters. It may help explain how separate extremes can unfold at the same time without being truly separate in structure. The 2023 Kornhuber paper carried the idea further by linking the 7-wave QR pattern to synchronized concurrent extremes, showing an association with simultaneous high-impact weather in multiple geographically separated parts of the Northern Hemisphere. The paper identified historical cases, including the 2010 Russian heatwave occurring alongside the Pakistan floods and the China heatwave, all during a documented QR7 wave event. It also noted that the 2018 European heatwave, the Japan heatwave, and the California fires occurred during a documented QR event. The 2021 Pacific Northwest heat dome, coinciding with Central European floods, is likewise described in the paper as QR consistent. Taken together, this body of work shows that the QR framework is not merely an abstract possibility. It has been documented, tied to specific historical events, and folded into the operational climate attribution literature. The peer-reviewed science offers a useful lens for understanding the kind of compound continental extreme weather pattern unfolding over the next 96 hours. That lens is the quasi-resonant amplification framework, or QR, and it does more than describe a pattern after the fact. It also points to a prediction that can be checked against the record. As the Arctic warms more quickly than the equator, QR-type events should become more common. The Rantin 2022 paper, which documents Arctic warming at 4 times the global pace, helps support that background condition. Meanwhile, the broader frequency of QR events across recent decades has also been examined in the literature, and the direction of travel is upward. Still, the science has an important boundary. The signal is not yet so strong that one isolated event can be formally assigned to the warming climate with confidence. What matters here is the accumulation. The overall trend exists, and it is moving the way the framework would suggest. That distinction is quiet but essential. It keeps us from turning a scientific framework into a slogan. It is also important, in the spirit of careful analysis, to acknowledge the limits of QR rather than treating it as a complete explanation. Climate dynamics researchers continue to debate whether quasi-resonant amplification is the main force behind the observed rise in compound continental extremes, or whether other processes are sharing the work. Those other candidates include shifts in storm track position, the expansion of the Hadley cell, and changes in the planetary scale temperature gradient outside the Arctic. The 2017 Mann and Ramsdorff paper, which first laid out the connection between QR and extreme weather, was followed by discussion in geophysical research letters and the Journal of Climate over how statistically significant the trend was. At present, the most careful reading is that QR is one contributor among several, while its exact share of the total signal remains unresolved. The framework is developed enough to appear in the operational literature, but it is not the entire architecture of the problem. That nuance matters, because public explanations of a week like this can sometimes make QR sound like the single answer. It is not. QR is one mechanism, storm track displacement is another, Hadley cell expansion is another. Large-scale temperature gradient changes beyond the Arctic are another. The rise in compound extreme weather appears to come from a combination of these mechanisms, with their relative weights still under scientific review. A fair summary would be this: the framework is real, the mechanism has been documented, and the trend points in the expected direction, but full attribution remains an active question in the peer-reviewed literature. That brings us back to the structure of the next 96 hours. What we are watching is one manifestation of the kind of compound continental extreme event that a warming background climate may produce more frequently. The relevant mechanisms are described in the science, the long-term pattern is documented. But this individual event, by itself, is not formal proof. The honest conclusion is that the atmosphere is behaving in a way the framework anticipates, not that a single week can prove the framework on its own. In science, the weight comes from repetition over time. Part 10. Coincidence or signature? The known pieces are already substantial, and they deserve to be held separately from what remains uncertain. We know that tonight there is a slight risk corridor from central Indiana through the upper Ohio Valley into southern New England, affecting 26 million people, with damaging wind gusts as the leading hazard and the peak window between 3 and 8 inches the evening Eastern Time. We know that HREF probability matched mean guidance tied to the slow-moving upper low over Texas shows a worst-case rainfall bullseye of 8 to 10 inches through Sunday morning, while the official Fort Worth flood watch is more conservative, advertising 6 to 8 in across the I-35 to I-20 quadrant. We know that the HRR significant tornado parameter in southern Saskatchewan and southern Manitoba reaches a peak value of 5.2 during the evening hours, in an area where that number is uncommon in early June. We know that 21 red flag warnings and 16 fire weather watches are active at the same time across 6 western states. We know that 18 separate river flood warnings are in effect across Missouri, Kansas, Nebraska, and South Dakota, with several moved to moderate severity during the past 24 hours. We know that the WPC extended discussion describes an unseasonably strong low-pressure system for June arriving on Tuesday. We know that for a possible Wednesday upper Midwest tornado outbreak across Wisconsin and Minnesota, the European model is markedly more aggressive than the GFS. We know that the first significant heat wave of summer is building across the central and eastern United States by mid to late next week. We know the sun contains 11 numbered active regions, with a 50% M-class flare probability each day for the next 72 hours. We know the ENSO state is warm, neutral, and trending toward what could become the strongest El Niño the modern record can measure by December. And we know that peer-reviewed literature describes quasi-resonant amplification as a mechanism capable of linking these kinds of signatures within one broader framework. The framework anticipates more events of this type as the background climate warms. Yet the record also contains severe weeks from before the warming background became established. Compound severe weather can occur even in a stable climate, and for any one episode, formal climate attribution is more difficult than identifying the aggregate trend. That is the dividing line between observation and interpretation. It may feel like a signature, but science asks whether the pattern persists beyond the moment. What we do not know is whether this week, considered as a single event, belongs mainly to natural climate variability, or whether it reflects QR events becoming more frequent. We do not know whether the 1936 megaflood year is the best historical comparison, or whether the 2011 super outbreak season is the more fitting analog, or whether 2026's bad week will be remembered as just another bad week. It is also possible that it will later be seen as one of the years when the trend became visible enough that the operational community could no longer look past it. That answer will not arrive quickly. It will come from the aggregate, and the aggregate needs a decade to settle. For now, in the real and immediate next 96 hours, the operational forecast should be treated for what it is: concrete, actionable, and separate from the larger attribution question. Tonight's outlook is crowded with hazards, and each one deserves to be treated as practical information rather than background noise. Severe convection is expected across the Ohio Valley. Central Texas faces a flash flood threat. Across the Canadian prairie, the setup carries the possibility of a large tornado outbreak. Farther west, critical fire weather is expected to persist across the mountain west for days, while rivers in the Central Plains are forecast to remain in flood through Tuesday and likely beyond. By Tuesday, an unseasonably strong surface low is expected to arrive. By Wednesday, the upper Midwest may be facing its own tornado outbreak risk. At the same time, the first significant heat wave of summer is forecast to expand over the central and eastern United States by midweek. In a week like this, the forecast is not a spectacle. It is a map of decisions. If you are in one of the severe weather corridors, know where you would shelter before the warning comes. Make sure you can receive a warning when it is issued. If flooded water is nearby, whether it is a creek, a bayou, or a river, do not enter it. Secure loose outdoor objects, including trampolines. Keep the weather radio close. Think through what happens if the power fails, and what you will do if the wind rises suddenly. None of this is new advice, and none of it depends on any special interpretation of the larger question running through this discussion. These are the basics of staying operational in dangerous weather. They matter tonight, and they will continue to matter through the rest of the week. Before we leave the forecast behind, there is one more issue to name plainly, because the discipline here is to meet conspiracy framings directly, rather than let them gather force unanswered. A week with multiple severe weather modes unfolding at once is exactly the kind of week that attracts those narratives. The claims tend to be familiar, that someone has engineered the pattern, that the federal government is concealing the truth, that aircraft contrails are responsible, that HAARP is driving the atmosphere, that Earth is being targeted, or that the sun is being weaponized. Those explanations may feel dramatic, but the scale does not work. The physics begins with the energy budget. HAARP operates at 3.6 megawatt. A single mid-strength supercell thunderstorm carries kinetic energy on the order of 10/16 or 10/17 joules. That gap is 14 to 15 orders of magnitude. In plain terms, it is like arguing that a flashlight could warm an entire planet. A very small energy source cannot plausibly command an atmospheric system that large. Cloud seeding is real, and it can produce measurable effects, but the pathway is limited. The Shira West Caldera Davis 2016 Environmental Research Letter Survey of 77 geoengineering scientists places precipitation enhancement in existing clouds, somewhere between 5 and 15%. That does not provide a credible route to creating a 95th percentile precipitable water stream over Texas, or an STP value of 5.2 over Saskatchewan. Aircraft contrails contribute approximately 3/12% of global radiative forcing, with persistent contrails making up only a small fraction of that. Meanwhile, the QR mechanism acts through planetary scale temperature gradient forcing, far beyond what aircraft can supply. The claim that the federal warning machinery is hiding the situation also collapses against the evidence in front of us. As of 1,509 UTC today, 235 active alerts had been issued, and the same forecast details discussed here are being broadcast publicly. The science does not need secrecy to explain the pattern. The conspiracy frames fail because they mistake scale. The clearer explanation is the published peer-reviewed framework. The QR mechanism, Arctic amplified jet weakening, high-amplitude stuck wave trains, and the compound continental severe weather events that can follow. That framework suggests more events like this in a warming climate. It does not require a covert hand to produce this week's compound setup. The mechanism is documented, and the atmosphere is behaving in a way that fits it. A calm reading of the evidence may be less sensational, but it is the one that takes the science seriously. That brings us back to the structural question at the heart of the whole episode. When 6 structurally distinct, severe weather modes are active across North America within a single 9-6-hour window, all tied to the same upstream atmospheric pattern, and all consistent with a published, peer-reviewed mechanism documented for more than a decade, how should we name what we are seeing? The question becomes sharper when those events unfold while broader Earth system signals are leaning in the same direction, and while the year is on pace to produce the strongest El Niño signature the modern record can measure. layered on a planet that has already crossed the 1.2 degrees C warming threshold. At what point does coincidence become an inadequate word? And when do we begin calling this the operational signature of the kind of compound, continental, severe weather pattern that a warming climate is producing more often? The next 96 hours cannot settle that question alone. The historical record has always contained severe weeks, and difficult clusters can occur even in a stable climate. Trends require time. The aggregate signal takes a decade to resolve with confidence. What we are watching now is one data point in a much longer chain, and that chain will take years to fully understand. Still, data points do not vanish. They arrive, they accumulate, and eventually they become the record. The central question is not whether the record will keep filling in. It is whether we are watching carefully as it does. This week is one data point. The next several years will bring many more. The pattern is loaded. The mechanism is documented. The framework predicts more. The Arctic is warming. The jet stream is slowing. The wave trains are growing larger. The pattern is locking more often. Compound events are firing more often. In quiet increments, and sometimes in violent weeks, the historical record is being rewritten. One final note belongs to the sky beyond the weather, because the asteroid catalogue has also been part of the spring and summer watch, and the coming week includes a small close approach worth marking. Asteroid 2026, LD, will pass Earth at 2.97 lunar distances on June 9th at 521 UTC, moving at 9.3 kilometers per second. It is a small object in the 10 to 20 meters class, comparable to the Chelyabinsk superbolide of 2013. The miss distance is comfortable. In a week filled with atmospheric intensity, that quiet detail is a useful reminder. Not every close passage is a danger, but every measured passage becomes part of the larger record we keep of a dynamic sky. The asteroid is not headed for impact. In the next 2 weeks, the nearest natural close approach on the watch list remains well beyond any level that would normally raise concern. The Tunguska-class object, the type that could produce serious regional damage if it entered the atmosphere, does not appear on the close approach list for this period. So the reason to mention it is not alarm, it is context. Viewers who have followed Calm Space for some time will recognize this as part of the background check we make during a compound event week, when the sky, the atmosphere, and the broader pattern are all being read together. That distinction matters, because a longer list does not automatically mean a more dangerous sky. What we are seeing is partly the result of a better catalogue. As detection capability improves, more close approaches are recorded, just as better observation can make a busy environment appear even busier. But the underlying impact risk is not rising in the simple way the raw close approach count might imply. The catalogue has become more complete. The sky itself is not becoming structurally more hazardous in the sense suggested by those numbers alone. Still, the work continues. We will keep following the asteroid catalogue, the atmosphere, the sun, the rivers, the endostate, and the published science. Week by week, month by month, year by year, the framework has to be tested against the data until the larger structural question is answered by the aggregate, not by a single event. That is the quieter discipline behind the forecast. For tonight, however, the operational message is much more direct. Severe weather is on the way, and it is expected to affect 26 million people across the Ohio Valley and the Northeast through Saturday evening. A slow-moving upper low over Texas is forecast to bring 6 to 8 inches of rain to a corridor west of I-35 through Sunday morning, with a worst-case bullseye of 8 to 10 inches still on the table. In the Canadian Prairie, the evening period carries the day's highest tornado risk. Across the Central Plains, rivers remain loaded, while western fire weather is expected to worsen through Tuesday and Wednesday. The Tuesday surface low is projected to be unseasonably strong, and the Wednesday upper Midwest severe weather setup could become a tornado outbreak. By midweek, the first significant heat wave of summer is expected to build across the central and eastern United States. Each piece is important on its own. Together, they suggest a stretch in which preparedness may matter hour by hour. So, treat the pattern for what it is. Follow the forecast closely. If a warning is issued, take shelter without waiting to see the storm. Secure the trampoline, make a plan, and do not drive into water on the roads. The federal warning machinery is there to function. Your part is to be ready when it does. The pattern is real, the events are approaching, the framework has been documented, and the question remains active. The next 96 hours will become another data point as it arrives. Pay attention as it lands.